Po-Feng. I'm postdoc. I joined here about 2 months ago, so maybe I haven't talked to many of you, and even we have talked, probably you don't know what I'm doing in science. So I think like today is my sort of self-introduction to about my science part. Yeah, so the title, Extragalactic Archaeology, it might sound a bit fancy, but yeah, that's just my trick to drag you to my talk. And what we'll introduce you is how can we use deep galaxy spectra to learn to trace the formation of the galaxies, especially for distant galaxies. When we study galaxies, usually we very often hear about the word galaxy evolution. But what evolution means? In dictionary, it means the way in which living things change and develop over a million years. So let's like say, we look at a galaxy at redshift 2, 10 billion years ago. Then we look at galaxies at redshift 0, and they look different. So what's the difference and why there's difference? And it also could mean a gradual process of change and development. Just like if you look at a galaxy in a very early universe, and if possible, you track the evolution, you see how it evolved, how it changed in all its parts. You look at a cat, you can monitor the life history of the kitty and watch it grow and age and sadly eventually die. So by monitoring the life history, you know very well how a kitty will grow up and how it will evolve. But sometimes the picture is a bit obscured, just like how a caterpillar becomes a butterfly. If you do not monitoring the life history, you'll never believe a caterpillar and the butterfly is the same thing. It's very hard to believe. Then how about the galaxies? How can you just easily believe that a spiral galaxy will turn into an elliptical galaxy? Right? They look totally different. And in this case, we're not able to monitor the life history of individual galaxies. It's a billion years. So it's not possible. How we derive this picture is we were doing a little bit different thing, using sort of a kind of indirect way. We are actually looking at the galaxy, so the population of the galaxy at a different cosmic time. We look at the galaxy population, a different snapshot, and we're trying to connect the dots. We're trying to figure out which group of the galaxies, as at redshift 1, will evolve and turn into the galaxies at redshift 0. And we try to find a good theory to explain this kind of a change. But in this way, well, it works. We've learned a lot, but doing this is like, okay, you're looking at the pictures of 2 groups of cats, and you're saying, well, I want to figure out which, maybe one cat in this picture, and it will, when you get old, which cat it will be here. And in this particular case, it's wrong. There are not just 2 cats. There are 2 different cats. And when we look at the pictures, the galaxies, or not pictures, just look at the galaxy at different cosmic epoch, basically the same thing. You're not looking at the same galaxies. But that's the fundamental challenge when we do galaxy evolution. As I say, we just cannot monitor the same object throughout its lifetime. So to study the things with a very long lifetime, we do one way. It's called archeology. You dig into the ground and you analyze the component going through the fossil record, and you somehow can reconstruct how this object evolved in a very, very long time scale. And we can do this to galaxy as well. So galaxy consists of many, many stars, just like this. And each star, if you can analyze them from its color, its spectrum, then this star, when does this star forms. So from this, you can reconstruct the formation history of the galaxies. But most of the time, actually, we are not able to resolve the galaxies into individual stars. Most of the time, we're looking the galaxy just like a very big and fuzzy blob. We do not have the spatial information, we do not, we cannot look at the single galaxies. So even we do not have the spatial information, the information in the wavelength is still there. So the galaxy light is essentially a combination of the light from all the component stars. So conceptually, if we can do a linear decomposition of the galaxy light, of the galaxy spectrum, into stellar spectrum, or in practice, the stellar population, the spectrum of different stellar population of different ages, then we can essentially reconstruct the assembly history of the galaxies. We'll know at what time, then how many stars form, and so on and so on. So that's the idea. The idea is that, but in order to do this, the first step is you need to have the data to do these things. You want to be able to track these absorption lines. You see all the absorption line strengths are different for stellar population of different ages, and you need to have those. So the very first step is take the data. So in the last few years, I and a few of my collaborators were executing a big observation project. We used the ESO, very large 8-meter, very large telescope, to take some high solenoid spectrum of galaxies around redshift 1. That's about 7 billion years ago, just roughly right in the middle of the evolution history of the universe. This is one example. You see all those wiggles and up and downs. They are not noise, they are really signals. You can see many absorption lines, strong absorption lines from several elements. And that will tell us the stellar population of this galaxy. So we take about 3,000 of them, and all the data is public. We make a public data release just a few months ago. So now everyone can use the data. And this is, so we take a 3,000, we hope it's a statistical sample and it's representative. You're not looking at some very special object, okay? So, so this is the data, and I will start with a showcase example and try to convince you that we can really do this from the spectrum, okay? So this is my example. This is the galaxy, average 0.8 or so. Well, our target is the one in the center. So from the image, you see it's interacting with the nearby galaxies. When we take a spectrum, it looks like this. So when we will try to reconstruct this formation history. What we do is we need first to make some simplifications. We assume that this galaxy, the form, has some constant star formation rates in some certain time beams. Okay, and then we allow all these star formation in each time beams freely goes up and down, and we just try to find the best linear combination and to produce a spectrum that fit the observation the best. So the red line is our best fit spectrum, and this best fit spectrum has come from the star formation history look like this. So this star formation history has kind of a special feature. It's this one. So it suggests that this galaxy, from the spectrum, has some intensive, elevated star formation activity about 1 billion years ago, 1 billion before we observe it, and it shut down very, very rapidly within, say, 500 million years. And this is nice because what this suggests from a spectrum actually is consistent to what we would have guessed by looking at images. This galaxy is interacting with the other galaxy, and theoretically, if there is a gas, this galaxy interaction can trigger this intensive star formation and then shut down the star formation in a short time. So we think, this is a good, this is good evidence that to show that yes, this spectrum really contains the information of the formation history of the galaxies.
So do you allow the methodicity to change?
Yes, but not in this particular fit, not in each beams. So here again, that's another layer of simplification. We assume the methodicity is the same for every time beam, but it can go up and down, but it's just one methodicity for all time beams.
And how robust is this star formation history?
That is a very good question, and yes. Right. I'm just to be honest. In this room, if you look at the papers, and you'll see many people do this, and will tell you, oh, how accurate we can get. But it will depend on, for example, which stellar population census model you use, what's the dust temperature curve you use, and even say here we assume some fixed time beams, and even you change the boundary of the time beam, it will change. So I do not have a simple answer to tell you how robust it is. I think, in my opinion, we'll need to do some recurrent tests. For example, you just put some random stuff from history and add some realistic noise and so on, and put your whatever assumption, and you see how well you can cover. However, this test is very, very time consuming. So at this moment, there's only very, very little work to do in this. So I think I would say this is an unanswered question. Yeah.
Is this derivation sensitive to the assumption of IMF?
Not for that, I would say not quite. The IMF is, of course, it will depend a little bit on IMF, but in my opinion, that's relatively minor. Yeah.
As you mentioned, there are several uncertainties. For example, that burst of star formation rate is going to bust.
Yeah, whether there is a burst, it is robust. But what I will question is, say how strong it is. It's whether the peak is 100 or 200. Maybe I'm not that sure. Whether it's like 1 billion years ago or 0.7 billion years ago, maybe if I change some assumption, it could have some, 50% of change. Yeah, but there will be, what I can tell you is robust is will be a burst in the relatively recent past. That statement is robust. Okay, so yeah.
So this is based on the wavelength range shown here, or
Yes.
you have a wider coverage?
For this particular fit, we only use this information.
So if you were to observe lower redshift ones, where you have wider coverage, would the reconstruction be more robust?
In principle, yes. But again, that's something I think no one have ever tested. Yeah. Okay. So yeah. So actually, I will start. No, I will continue the science topic from this kind of object. So this kind of object is a special object, and actually they have a kind of name called post-starburst galaxies, and it's sort of obvious it's after a starburst. Okay, so this special galaxy they are identified traditionally. They are identified through spectrum. They are Poisson galaxy. They are not forming star right now because you do not see strong emission lines here, and also the significant feature is the strong Balmer absorption series. That means this galaxy is dominated by A-type stars. That tells you a few 100 million years ago the star formation rate was high, but it's not forming right now, so its star formation rate is low. So therefore you think there's a star burst in the recent past, and this object is interesting is because there might be a process which can tell you what is the physical mechanism would drive this kind of a truncation of star formation. We hopefully something or some physical mechanism truncate the star formation happened relatively recently. So if we look look at these galaxies closely, we might be able to find out what is the mechanism. So I spent some time to do this kind of studies, and like one thing I've done recently is I collected a sample, and I find somehow for these post-starburst galaxies, the size and the optical and infrared color, they have a correlation in such that those are the most compact ones are also they also have the bluish color. So their formation, maybe the star formation history, is somehow correlate with their structures. I will just jump to the conclusion. I will skip the how do I search for the answer. I will just tell you the most plausible scenario I think. And actually it's kind of a simple and straightforward. So let's say we start from a galaxy that look like this. And from the previous slide, okay, this galaxy is very likely they have some starbursts. They form some new stars. So if I put these new stars at the center of the galaxy, what would happen? It will become bluer. And also the light is more concentrated in the center. So if you measure the structure defines the effective radius, it will also become smaller. And if you put more and more new stars, it just become bluer and bluer, and the effective radius becomes smaller. So that's a very simple scenario that how can you create this kind of correlation. Okay, so the next thing is I also took some follow-up observations for these galaxies to try to see whether this scenario is plausible. So I was able to get some ALMA data to try to measure the CO221 line, the molecular trace, the molecular gas. So I want to know the molecular gas is the raw material to form stars. So I want to see whether this is the gas, where these raw materials are in these galaxies. So I was able to observe 5. These are not very cheap observation. Each one will take 2 to 3 hours. I observed 5 of them. Then 3 of them are clearly detected. And for these 3, although the angular resolution is not superb, it's like this. But what we can say is it's consistent with being at the galaxy center. But also I want to point out like this one. This is like 3 sigma, very weak detection of center. So maybe the whole story is not like totally like simple and straightforward. But for these 3 clear detected cases, we find the molecular gas is at the center of the galaxy. And then the bottom row is the continued emission and 3 gigahertz observed by the very large array interferometer. So we dig out the archive images. No, I think I will take off my mask. We dig out the archive image. So the 3 gigahertz continued emission, you could trace the star formation. And the angular resolution in this map are much better. It's about 0.7 arcsecond, corresponds to roughly 5 kiloparsec at this redshift. So under this resolution, whenever it's detected, it looks like point sources. So if it's traceable by star formation, then it is really the last period star formation is really being at the center. But notice that this could also be the radio emission could also be from AGN, and that unfortunately for that part we are not able to tell. Okay, so all this information we get together, we think we see a strong like empirical constraint that if the star formation of the galaxy is truncated, then it is very likely accompanied by intensive star formation activities. And that star formation activity should happen at the center of the galaxy. So here I do not tell you like anything about what the really like driving mechanism is. But this is the empirical constraint. You can invent your favorite idea, your favorite theory, but that's something probably you have to reproduce in your theory. Okay. So yes.
Sorry. So from the O2 light and the full spectrum fitting, you can estimate the potential contribution from an AGN?
That is I think it is a different question because you say you look at all the AGN and all those say agent features, they are not always correlated, right? You see some AGN have optical emission line, but they do not have radio or X-ray emission and vice versa. So for individual galaxy, I think we can't. We can say it's more likely, actually for these galaxies, it's more likely they have AGN by looking at statistic. Usually they have some frequent, they have some O2 emission. They have it's more likely they also have radio emission and X-ray emission if you compare to say normal quasar galaxies. But for individual galaxies, I think we can't. We cannot say for sure.
If you observe those galaxies with VLBI, does it help?
With what? Sorry.
If you observe them with VLBI, very long baseline interference, does it help to identify if they are creating star formation or radiation activity?
I don't know, but for this particular galaxy, I'm not sure whether VLBI will have enough sensitivity. I don't really know.
HSA.
Hmm?
HSA sensitivity, right?
Yeah, but I don't know. I don't know what sensitivity. These are, say like this one. They are really like low level. This is in the cosmos field. The deepest VLO map.
Right, HSA contains VO. Yeah. So it's more sensitive.
Oh, okay.
Oh wait, there is no receiver. GPT, so just GPT plus VO.
Okay. Yeah. I have no idea about that. Yeah, but anyway, like these three is I can only see them with the deepest the VLO map in the cosmos field.
I guess Vanessa in the PDR's catalog, she provided some of the text about whether the sources could be AGN or not, and radio AGN, infrared AGN, X-ray AGN, IR AGN. Have you checked?
No, I do not check, but I think that fall back to that's the same issue. Even if you see that it look like say. If it has an AGN feature in say other wavelengths, then we may think there's AGN. But I think if even we don't, we still. I think I still wouldn't say that it's not an AGN, right? But I haven't checked that. Yeah.
So this fact is come from the cosmos field, right?
Yes.
So I think the cosmos field is quite comprehensive to answer which kind of a weight that AGN identifies.
Yeah. So I think you get all those catalog and you do a cross match,
But,
and you'll find they are not consistent, right?
yeah,
That's the natural.
But my question is, does this come from your original 3000 VLT spectrums?
Yes.
Okay. So what's the criterion or the major science you want to solve with your VLT proposal? Did you select from advanced or select from certain level criteria?
Right. So for the simple selection is observe the K-band magnitude. And the purpose is that we are not trying to select any special type of galaxy. We want to, as I said, we want to have a representative sample of galaxies. So we'll tell you, if you look at this galaxy, this is how the universe at Redshift 1 look like.
Okay.
Yeah. Right. So that's the choice.
Exclude any agent, you just include everything.
Yeah, include everything. So, so that's the purpose that we think, or the purpose of the observation is to produce a general purpose of data set. Yeah.
Your AMA data didn't detect continuum?
No. Yeah.
There's some chance of AGN.
Yeah, but no, it's not. This reference, it's right. Right. We don't see continuum. So what is the next step? We can try to do more observations, more follow-up observations, but you have to know it's gonna be difficult. This high Z, well, not really high Z, but distant object. They are faint. And also, if we think there's some there's some some gradients of their stellar population, you want to resolve them, and it's not easy. So my idea is that could we find some local counterparts of these distant post-diverse galaxies? And you will say, well, it should be simple. There's a lot of data in the local universe. And the answer is both yes and no. We do have a lot of data. For example, for identify these galaxies, I want to use the spectrum and say Sloan. It can have, say, 1 million of galaxy spectrum. But at the same time, if we want to, say, spatially resolve them, we want to look at very nearby objects. So if you take a spectrum, Sloan spectrum, then you are looking at the very center of the galaxy, maybe only looking at the center 10% of the light. But if you move this galaxy, you put this galaxy at redshift 1, and in normal oscillations, normal spectrograph will cover the majority of the stellar light of these galaxies, maybe 60 or 70%. So you're not looking at the same thing. But luckily, recently we have a solution. It's the IFU survey, like SDS Manga and others. These are the spectroscopy surveys using a very large, have large field of view. And the best thing is that within the field of view, each point you get a spectrum, so you have a spatially resolved spectroscopic map of these galaxies. And they cover, for this observation, it's designed to cover a very big chunk of the stellar part of the galaxy. So that is the data set that I can use and try to find the local counterpart of this high redshift post-diverse galaxies. So what I do is actually quite different from maybe 99% of people who use this data. Or you can say this is kind of a very stupid first step. Yeah, I throw away all the spatial information. That's the people like the most, but my first step, I just don't want that. I sum up all the light in the field of view and make one spectrum per galaxy. So I use this integrated spectrum to identify my object. Like what I'm trying to looking at is the strong Balmer absorptions and relatively weak emission lines. So that's the spectrum feature I want. I do not want them have a current star formation, but with recent strong star formation in the recent past. Okay, so I can identify only 9 out of like 4,000. These are very rare objects. Then after that, I can get special information back, then look at the spectrum in different places. For example, this one has an emission line center, and the outskirt is more like the sort of post-star burst-like spectrum. So to give you a quick overview, I will color-coded this galaxy into 3 different colors. Those in blues are regions with clear emission line, like this, and those in greens are those sort of post-star burst spectrum, strong Balmer line but no emission lines, and the rest in red are spectrum look like, say, quiescent galaxies. They are older. Those regions have older stellar population. And the very quick overview of my 9 galaxies look like this. I just want to point out one thing, is that if you look at the center of this galaxy, you will see many of them actually have an emission line center. So this tells us 2 things. The first is this feature is actually similar to the post-star burst galaxy we see in the distant universe. We think in previous those things, we think the last period of star formation should happen at the center, and if it does, then this might reflect as like this. In the center, we have some emission line region.
So when you do this, you already excluded the narrow line regions from it.
No, and I will talk about that. Yeah. So the second thing is that if you want to try to find the local counterpart, you really should not use the fiber spectrum, because like for half of them, if you look at the center, If you look at fiber spectrum, you will think they are emission line galaxies, and you think, oh, maybe there's a star formation, so you will reject them from the sample. But for all these galaxies, if you put at redshift 1 and observe with a normal, a typical instrument, then it has the post-starburst like spectrum. Okay, so yes, we see the emission line in the center. So what drives the emission? What ionizes the gas? So here we're looking at the H alpha flux density as the function of radius in units of arc second, and is normalized by the H alpha flux density for each individual galaxy at the center, right? So when I plot this and I saw this, I thought, well, I probably did something stupid in my plotting script because they look all the same. But soon I realized I'm looking at the point square function for the manga observation. Basically, they look like the Gaussian for we have maxima about less than 3 arc second, and that is the point square function of manga. So essentially, almost all of the emission in this galaxy should be intrinsically compact. The size must be smaller than 1 kiloparsec. So all of them, almost all of them. And yes, some of you will think, yes, and I know the origin. Point source like emission line in galaxy center and those galaxies are not supposedly quiescent, so it must be AGN. And we can look at this by checking some strong diagonal line ratio, the very commonly used O3 over H beta, N2 over H alpha, and S2 over H alpha, to use this emission line ratio to understand, to tell whether the gas is ionized by star formation or AGNs. So for these galaxies, if we look at the very center, which is the central 2 arc seconds, which is this pink circle, yes, it's dominated by AGN. But for the second galaxies opposite, the center is dominated by star formation by H2 region. And actually, most of them, like 6 out of them, have the star formation center. It's not AGN. It's not what do you think, say some compact emission line at the center, galaxy center is AGN. No. So again, I think this just draw the similar picture to what we think for those distant post-starburst galaxies. If you truncate the star formation in a galaxy, then you will probably have some, the last period star formation would happen in the center of the galaxy. And also, since we see this similar feature in the local galaxy and the high redshift post-starburst galaxy, so I think these are much easier to observe. So maybe if we can understand how do we produce, how do we make these low redshift post-starburst galaxies, and we will be able to just apply this knowledge and explain what has happened at high redshift. So we do not need to do those very expensive and maybe challenging and maybe impossible observations. So.
I know the orientation of the galaxies, are they mostly kind of based on?
They're among the 9 galaxies. There are like 1 or 2 face on. There are like 1 or 2 is totally edge on, and some inclined. It's everything.
But do you see any difference between the face on and edge on ones? Because you're looking through the ring or something.
So what specifically? What kind of differences are you referring to?
You know the AGN, the unified scheme will have this accretion disk in nucleus.
Yeah.
Torus.
Yeah.
You view through the pole or through the disk.
Yeah. Okay. So I did not really check this, but I can try to share information from my memory. Like this one is totally face on. This one with Asian dominant center. This one is face on. But there is another. Yeah, there's 2. So the other is basically edge out.
Sorry, I thought you have 9 galaxies.
Oh, but one of them, the actual alpha emission is too weak. Yeah, so only eight galaxies I can do this. Yeah.
So what are their environments?
Two of them are in the coma cluster. Yeah. What, or do you want to know like more?
I thought you want to know how their star formation is shut down. So environment presumably will give
Right.
you something.
Right. So like for in general, when we look at the post-diverse galaxies, yeah, people would think, right, in the cluster you can have this thing, right? But you see this kind of galaxy everywhere, not only in clusters. And in clusters, you do find more. So that's other sort of information that may tell you, okay, in clusters something more. So there might some extra mechanisms. But even outside clusters, there are some mechanisms to do this. And yeah, I have some idea about that, but unfortunately this is not covered by today's talk. Yeah.
Are they in pairs or?
No, they are not.
So, do you have the K-band or H-band image for all of them?
I do not check that.
Is it possible to do the surface index decomposition to check the central region is contain the suitable or not?
Okay, yeah, it must be
It
possible.
would be interesting if the center is like already is like is very old population, probably they have just followed a certain index of 4. So if you found the emissions, then it will be interesting.
Okay, thank you. Yeah, I did not do that. Okay, yeah, so right, so that's the yeah, so that's what I want to say about these special objects. But the next I want to bring you back to the more like general purpose of the data set was that since for each galaxy we can do those star formation history reconstruction, and we have a representative sample, so like combined all the individual galaxies, we can say show what's the mass assembly history in the universe. Right? For example, yeah, here we are looking at the galaxy of the different stellar masses, and the growth rate as the function of the age of the universe. So here we see that on average, more massive galaxy accumulated stellar mass at an earlier time, and for slightly lower mass galaxies, they are not really growing. Their main period of mass growth is more recently. So there's a mass dependence. Or you can look at other parameter. For example, here we are slicing the sample in by their velocity dispersion of the stars. That trace the total gravitational potential. So you can think that's a tracer or proxy for dark matter halo mass. Again, we see that the galaxy in more massive halo, they accumulate stellar mass at early time, and those live in low mass halos, they grow at later times. So actually, this is not totally new. That we see, okay, more massive halo in the galaxy, they do form at early time, and this is not totally new. We have some, like this field, people doing the galaxy evolution have sort of derived this in the last decades. But it's nice that now, I think that this is more, say, straightforward way. We really trace the formation history of individual galaxies. And it's nice that to see, okay, we got something sensible and the consistent result from the general knowledge. Then, since we have a lot of galaxies and we can expand this kind of a search, not looking at not only one parameter, but here, say, I add another dimension. Here is the stellar mass, the same, but the actual dimension is the size of the galaxy. And we're looking at here. We're looking at only the quiescent galaxies. And the color coding is according by their stellar ages. Here roughly tell you what's the main, when did a galaxy at a given mass and size accumulated the bulk of the stellar mass. Okay, so we see some trend here. The first is what we just see, more massive galaxies, they have older stars, they form earlier. But in addition to that, we also see that compact galaxies are average older, except for these guys. We'll not look at them. Actually, the post-diverse galaxies, those weird guys, they tend to be here. So those are some sort of special guys. But if we just block it, we'll see we see that basically the two trends, more massive and compact galaxy, they form earlier. So I think we are looking at, what they're telling us is to first order, the gravity really control the evolution of the galaxies. And this, you can imagine that if you start from a more massive and compact halo, the gas will collapse at an earlier time. So gas will turn into a star earlier time, and maybe a central massive black hole will grow up faster, and the feedback will kick in earlier. So everything just happened at an earlier time. And so the galaxy evolution is, how fast the galaxy will grow is basically we're seeing the imprint of their initial condition. So like by tracing the age of these galaxies, we'll be able to get some statistical view of how the universe is evolved.
What does the population look like here? How many galaxies do you have at the low end and how many galaxies at the high end? So for all, on this part there are more than 1,000 galaxies. And how many in each place is? Do each cell have the same number of galaxies?
No. Yeah. So maybe like 10 to 20 per cell in this region, and maybe a few here, or maybe 10, less than 10 here, I think. Yeah.
We thought about bringing the dynamics and plot it as third axis.
Yes. I don't have the plot here, and it's a bit complicated. But
You see a surface.
A surface with large scatter. Yeah. Okay. So here's a statistical view, and next we want to look at what. So we think from the data we have a good statistical view, and the next thing is that we're thinking, okay, the current large-scale simulation, actually they are doing amazing things. The most state-of-the-art cosmological hydrodynamical simulations, they are now trying to reproduce, not really reproduce, but they are simulate the evolutionary universe. They start from initial condition, take it into account gravity, theoretical physics, and just let the computer to do the work and produce a mock universe. And in this simulation, they save a lot of information of the gas distribution and the metal content and the growth of a supermassive black hole and so on. So we're thinking, if this simulation is really doing so well, then maybe we can just find a galaxy of interest in the simulation, and we can trace the evolution because everything is recorded. And there are some property that is very difficult to get from observation, but it's recorded in the simulation. That will be wonderful, but the first thing is we have to make sure that this simulation is doing the right thing. They really produce the galaxies that look like the real universe. And in this simulation, they do this sort of control, the calibration. They start from the redshift 100 and that evolve, and they essentially what they do is they show that they can produce reasonable galaxy population at redshift 0. But if you start at the right place and at the right place, that doesn't mean that you're taking the right path, right? So it will be better if we can test somewhere in the middle. And so that's the motivation. We think, okay, our data is so good. I think So we should be able to test the simulation. We should be able to validate the simulation to see whether they are doing a sensible thing by putting a comparison point, putting an anchor at the middle of the evolution history of the universe. So we decided to team up with the Illustrated TNG project. This is one of the best and largest hydro-dynamical cosmological simulation. And the reason to choose to team up with them is straightforward, because the PI of the Illustrated TNG was my colleague when I worked in Germany, and her office was just 10 seconds from mine. So it would be shame that if we don't collaborate, and then we do. And for this, actually, I sit in her group meeting for a year and a half. So what we're doing, so we're trying to make a comparison, but this is actually non-trivial because simulation does not directly give you observables, say colors or spectrum. What they give you is for each galaxy, they have the component stars, and for each stellar particles, you know when the stellar particle forms and what is the chemical, what is the metallicity, what is the chemical composition it is. So we need to take this information and do some post-processing to make the spectrum. And then we need to make it not so perfect. In real world, there are noise and all other things. So this is our final product, the final Mach spectrum. And I think you could appreciate like visually, they look pretty, they just visually look like the real observations. So then we can try to make some comparison. But even then, it's not say trivial. It's not like very clear what to compare. You can do many things. But for the very, very first look, we decide to do almost the simplest things you can imagine. We just take a very small part of the spectrum and track and to look at some particular spectral feature. Okay, so one of them is this absorption line. This is one of the Balmer absorption line strengths. And the other one called the 4,000 angstrom break. That's the flux ratio between the two continuum region around roughly 4,000 angstrom. And that's when the galaxy evolve, basically these two indices will evolve along with the age of the galaxy in this direction. So we just measure these two indices from Mach spectrum and from real observation, and we plot their distribution on this two-dimensional space and to see whether they match or not. So to first order, actually the simulation, which is the black contour, actually matched, I would say, reasonably well with the observation, which is the blue contours. But you probably already find it, there is some offset. So that means actually even the simulation, the one of the best, the cosmological hydrodynamical simulation, they fail to reproduce some galaxies in real universe. So what kind of star formation history of the galaxies here?
Is the abundance evolution taken into account?
In the simulation, yes.
How do we know if it's the cosmological simulation that's wrong, or it's the stellar population synthesis model that's wrong?
That's a very good question, and the answer is that we don't know. Right, we really don't know, and so that will be, in my point of view, I'm doing this, and in my point of view, that will be the very big and important field that have to be solved in the next 5 or 10 years, because now you will see like we could use this technology to say probably the very early universe, and like people get excited about it. But yes, if we do not know our stellar population synthesis model well enough, then we don't know what's accuracy we have. Yeah, and this is at the moment it's totally unknown. Not totally, but really like unknown, I think. Right. So yes, let's just take the face value here. There's the differences. So what kind of star formation history of the galaxies here? So I just show you a schematic figure here. We find that if you want to populate this parameter space, then the galaxy have need to have sort of a kind of a peculiar formation history. That this galaxy here, they formed the bulk of their stars several billion years ago. And they're quiet and they're not really growing right now. But they have to have some young stars, maybe something like 0.5 billion years ago, and really only a little bit, a few percent. You cannot be like too much. So we think, okay, so first from observation itself, this tells us the quiescent galaxy here, actually they are not always quiescent. They can form the bulk of the stars earlier time, and they become quiescent, not growing, but every once in a while, maybe every say, billion years, they need to have some weak, or maybe not they need, they just have some weak new star formation, and just really weak, a few percent. So in order to explain that why we see most of the galaxies, observed galaxies populated this place. So this is sort of the weak rejuvenation events should be common in quiescent galaxy at redshift 1. And we're also like, after we really convinced that this is the only explanation, then we think yes, then it's nice that the data is testing the simulation at the person level precision. So overall, the simulation is doing really well, but what they're missing is those like these small things. And you know, when I show this to the simulation teams, and they're okay with that, and but for them, it's like that's where we start to learn new things. Now they can go back, you know, to look at the model and try to find out why do they miss these small things. So that's nice. When by comparing the observation and the simulation, we are able to find out in which direction we can improve our theory of galaxy evolution or the implementation of their simulation. Yeah, so I think so more and more things will come, but at this moment, like some of my Italian colleagues are very happy about it. So they make a press release in their institute, but the funny thing is that it's about my work, but I do not understand it at all. It's only in Italian, there's no English version. All I can do is, okay, this I can identify keywords. This is our project name, this is my name, my institute, and that's it. So yeah, but okay, looking at this, I think, well, I now really have to work on it, otherwise I will let down my Italian colleagues. So yeah, the very last part, so what will be the next? Actually, this is kind of an expensive task. So we take those high signal noise spectrum of galaxy at redshift 1 using an 8-meter telescope, and we use like a 20-hour on source integration time. So this is really expensive. So what is next? We're looking at redshift 1, but if you want to say push to even earlier universe, it's kind of possible. For example, there's a data to observe this massive quiescent galaxy at redshift 4. It takes 8 hours on the Keck atmosphere, the most powerful telescope plus the near-infrared spectrograph. It takes 8 hour integration time to get something like this, something useful. You can see the Balmer absorption series here. And you combine with the broadband photometry, and you model them, you really can get some constraint on the star formation history. For example, these guys, it forms at, it basically, from the model, it formed within a few 100 million years. And the average star formation is a few thousands solar mass per year. And then we have to figure out how, right? So you can do this, but it will take long time. And luckily, but still it's possible. So luckily, like last week, my collaborator and I was informed that we get 2 nights of tech time to follow up this candidate quiescent galaxy redshift 4.7. Again, we want to confirm that from the SED fitting, it seems like this is a quiescent galaxy, and this, again, it's intriguing because at redshift 5, you think that the universe is very active, star forming, but somehow there are some galaxies already stopped forming and they don't want to grow anymore. So we want to first confirm this, and hopefully we can constrain the star formation history as well. Yes, so doing this at very early universe is possible, but it will take a long time. Like this one will take like we estimate we need 18 hours. So we hope in coming future with the 30-meter class telescope, we will be able to observe more of these objects. The integration time will be not 20 hours, but maybe 2 hours. So we can get really a sample, not just looking at the one or two special objects that we find. And the other dimension is that if we do not push to the very distant universe, we still in a more, still not local, but not that far away, we can get more information with next generation multi-object spectrograph. So this is what we have with our legacy project for galaxy at redshift 0.8. We get a spectrum around redshift 4000 angstrom. But for example, if you take the Subaru prime focus spectrograph to observe the same galaxies, of course this beast can observe like 2000 galaxies at the same time, so you can get much better statistics. But the other thing is that it also observed a much wider wavelength range, so it's possible to get more information in one shot. So you can get there are some stellar age and metallic tracer and also the gas properties. So hopefully we will be able to combine all this information and get a more complete picture and to inform us on how galaxies form and how galaxies evolve. So that might be some future prospect. So that's basically all. And the very final note is that the legacy survey data is fully public. All the science ready spectrum is there. And we also provide a catalog with some measurement, for example, observation line strength and velocity dispersion of stars and etc. So if you have any idea, you can just go to download, Google it, you should find it, go to download the data and do your analysis. But I would suggest that you can talk with me first. I should save you a lot of time by telling you what is possible and maybe what is not possible, what is promising and what is not. Okay, so that's all. Thanks for your attention, and I'm looking forward for more discussions.
Thank you very much. Questions?
To what extent are galaxy mergers important parts of the star formation history?
Yeah. So I think it's, in my opinion, that should be the main mechanism to produce these galaxies, to produce the post-starburst galaxy. That trigger a star formation, trigger intensity star formation and shutdown. So what we do is that, for example, if we identify this post-starburst galaxy and we can look at the images. If you look at really deep images, then you often find some tidal features or some nearby objects, like this one. But of course, it's just one. And again, there are some galaxies, some of them you don't see the tidal feature, but there's a high fraction. If you look at really deep images, you'll find something. Yeah. So.
Well, for example, the star formation curve at the end there with that little tiny blip, I can imagine that blip is from a tiny galaxy falling into a BCG or something.
Actually, I think that's not, because if that's the case, so what we're tracing, so more specifically, use this technique, what you're tracing, you're measuring, what you're measuring is, you're measuring the stellar ages. So if it's something falling, then for these things, the stellar ages you measure is not the time it falls into the galaxy. Right? It's when these things forms. So even you can fall in say just yesterday, but if this guy is like formed 5 billion years ago, then you recover something like maybe here. Right. So it's not the right. So it's not the mass assembly history of that one. How should I say that?
Right. So it's not. Yeah, basically you're tracing the stellar ages of distribution. So it's not like really.
But that's under the assumption that it's all joint mergers.
Right. So. Yes. So, but if you what you say is like something falling in, right? That means these small galaxies or stars already formed somewhere, maybe.
But you cannot exclude the possibility that it contains gas.
Right. So it's possible. Right.
Yeah, so the gas of the minor could trigger new star formation in the bigger galaxy, which would appear like younger stars.
Right. Totally. You're correct. Yes. And you say a few percent for those 10 to 11 solar mass galaxy. That's say 10 to 9 solar mass. I can totally imagine there are some smaller ones falling in and trigger star formation at that mass.
But you said your local manga galaxies, mostly live in isolation.
Right.
So where does merger come in?
Well, if it's already happened, then it can be isolation, right? But the weird thing is that no, I don't have the slide here. If you look at local manga galaxies, and their dynamics are not highly disturbed. So I still don't know like how to explain that, or I do not have I'm not very sure. But for those manga galaxies, what I do not show is only from those IV data you already can do like many things. Like for example, looking at dynamics, it's not disturbed. So if it's a merger, then it must be sort of a very minor merger. It cannot be, say, major merger.
So manga data is now fully published, along with a lot of value-added catalogs, including bulge disk decomposition that Amy mentioned. So you can just look at those galaxies. Other questions? You go first.
Is there any equations can combine these two graphs? Because I want to ask that other people can reproduce this result.
There are, so to do this now, just in the last 2 or 3 years, there are multiple codes. Yeah, there are public code. So in principle, yes, everyone can reproduce this. If you download the code, feed in the data, you should be able to get something like this. But again, just for earlier question, maybe you get the age of the burst would be a bit different. The strength of burst will be a bit different. But for this particular case, I am pretty sure that whatever code, whatever assumption you use, as long as it's sensible, you will get something, get a recent burst.
Outdoor operations, right?
So in the next slide, what are the star formation rate views? The next one, the post-star burst radio observation.
Oh, okay.
I just wonder if you assume that the radio emission is from star formation, what will be the corresponding star formation rate?
Right. So, let me talk about, say, for this one, this is a radio AGN. This must be an AGN. If you can convert that star formation rate, it's like 3,000. So, no. But this are like 10. This three are like 10. And there are like 10 to 11 solar mass galaxies.
You mean the century will be 10 solar mass per year?
Yeah.
Okay, but from the spectra, you don't see emission line, right? It's purely post-star burst.
Yeah, very, very weak. Very, very weak spectrum from the. So, yeah, I also can derive the star formation rate. Not that I can. We have star formation. We have the emission line. So if you look, you can sort of get some estimate. But the problem is we don't know well about the attenuation. So we see some emission line. If you convert that without correcting for the dust, that's like 0.1 solar mass per year. But that could be dust, and that could give you like a 10 times, make it 10 times higher. Yeah.
And how about the manga systems, those one with center
Oh, I don't remember the star formation rate, but I can tell you it's probably like 2 or 3 times, say above the Green Valley. If you get the Green Valley galaxies, then it's probably 2 times of that.
You mean higher or lower?
Higher, 2 or 3 times of that. Yeah. So if you put that region in, say, star formation and quiescent region, they'll probably live well in the star forming sequence.
Okay, so I think this is a good time to stop. Po-Feng will still be here, so you